Hello, this is Dr. James Camp from Lee College in Baytown, Texas, and these are my comments on structured data in C++. This is chapter 11 in the Tony Gaddis book, starting out with C++. Okay, so far when we've wanted to combine data, we've had to combine all of the same kind of data. So if we wanted numbers, we could make numbers point to an array of memory boxes that held 12, 14, 32, 42, 21, 19. Okay, but they all had to be the same kind of number. So this would have to be type int nums. Okay. What if we wanted to hold something a little bit different? What if we wanted to create a variable called student, and we wanted the memory box to look like this? We wanted to have a student ID 1, 2, 3, 4, 5, and then we wanted to have a student name. So a bunch of character variables here making up a string, and then we wanted to have a GPA, so 3.65 I'll say is my GPA. Okay, we can't do that with an array. What we can do is make a struct. A structure is a C or C++ construct that allows multiple variables to be grouped together and referred to, not just referred to, but moved around, passed to functions, passed back from functions as a single variable. This is especially powerful when you want to get some data from a function, and as you know in C++, you can only return one value at a time. But if you group all of your values into a struct, you can return them all at a time. Okay, so here's the example of how that struct would look if we were doing the student object we were talking about. Not an object, sorry, that has a specific connotation in C, but if we were making a student struct, we might have int student ID, we might have string name, we might have a short year in school, because your year in school is 1, 2, 3, or 4. You don't need a whole integer for that. And then we might have something completely different, a double GPA. Okay, each one of those takes up a space in memory. But what we end up doing is creating one big memory box and calling the whole thing student, and then we stick student ID in here, and then string name takes up however much space, really. Probably that's just a pointer to the string, but maybe we store the whole string there. Year in school is a short, so it doesn't take up that much room. And then GPA is a double, so it gets a bigger spot in there. Okay. Note that you must have a semicolon after the closing parenthesis. This is not a function, this is a type declaration, and in C++ those have to end with a semicolon. Struct names commonly begin with an uppercase letter, but that's just convention. You can use a lowercase letter if you would prefer. And multiple fields of the same type can be in a separated, comma-separated list. So I can say struct person info has string name, street, city, int, zip code. Okay. And then I have a semicolon. The struct declaration does not allocate memory or create variables. So it's just a declaration of a type. To define variables of the struct type, you use the structure name in place of a predefined type name. So where normally we would be typing int num, in this case we're going to type student S1, okay, or Bill up here. Okay, you may be wondering now, okay, if we put all of this stuff into the structure, how do we get it out, or how do we get it in the first place? C++ provides, and as do most languages that deal with structs or objects, a dot operator to refer to member variables of the struct variable. So if I previously declared student stu1, then I can refer to stu1 dot student ID, and that whole thing here acts as an integer. That's the whole name for that integer variable. So cin can take an integer from the console and stuff it into stu1.studentID. I can also then get line stu1.name, and that's going to read from cin a string that it will add to the stu1.name string variable. I can use the equals assignment operator to stuff 3.75 into student1.gpa. Okay, all of those are just accessing one part of my struct at a time, and then they behave like normal variables. Okay, this shows a program that cin's employee.imp number, then get lines employee.name, then calculates employee.gross pay is employee.hours times employee.pay rate. Okay, and then it couts a whole lot of variables. Note, you can't just cout employee. You have to cout the individual member variables. Okay, so if I cout Bill, that's going to produce, it might give me a string of numbers that are kind of meaningless gobbledygook to me, or it might just choke and say I can't acquire a value from that, and it wouldn't compile. But I can cout bill.studentID or bill.name. Okay, those, again, this acts like a normal variable. This acts like a normal variable. This does not act like a normal variable in this case. Okay, also, sad but true, you cannot compare entire struct variables directly. Okay, Bill does not equal William, but we can treat the member variables individually, okay, or field, and they're called member variables or fields, member fields. There are various names for them. One thing we can do that's pretty cool is we can initialize a whole structure at once, kind of in the same way we initialize an array. You do an open curly and a close curly, and in between them, instead of having a list of the same kind of number, which you would have for an array, you have a list of values that matches the list of fields that you defined in your student struct. Now, they have to be in the right order, okay? I couldn't take this student ID and decide to initialize it after the name, okay? That would not work. I have to put, if student ID was the first variable I declared in the struct, it has to be the first thing that I initialize in my initializer list. You can initialize only the first member or only the first two members. You cannot skip over one in the middle and then initialize the last one, okay? If we're going to do this, we have to provide a year in school. So if we don't know what it is, we can just put a 0 here and come back and fix it later. So here we are initializing a couple of employees. We put name first, then employee num, then pay rate. So we have to initialize name first, then employee num, then pay rate. Poor Jill, she doesn't get paid as much as Betty. Structures can be used in arrays, okay? So we can actually create, let's say I have a struct circle that, well, circle's too easy. Let's say I have a struct rectangle that has double height and width. Okay, might also add perimeter and area to it, but for right now I'm just going to have those two. Okay, then I can set up one height width, and then I can set up another height width. I can set up another height width, and this whole thing becomes an array of, so this would be defined as a rectangle of 3 and call it, say, rex. Okay, and then I can get this one by saying rex subscript 1 dot height. Okay, I can get the whole thing by just saying rex subscript 1. If I want just the height, I add dot height after my square bracket operator. Okay, this program uses an array of pay info. Okay, each worker gets hours and a pay rate. So we define workers, and we have 3 workers. And we get the employee data by stepping through from 0 to num workers, and we input workers index.hours. Okay, again, this whole thing acts like a normal variable. Workers at index.hours is just an integer. Workers at index.pay rate is just, well, that's going to be a double, right? Okay. And this shows you how you can take in those numbers and then use them to calculate gross pay for each employee. Okay. Nested structures. This is another pretty cool thing. Structures can contain another structure. Okay. If I had struct oval, which again has height and width. I left off the type there, silly me. Okay. Have to be double height width. Okay. I could have another struct snowman, which contains oval head, oval body top, oval body bottom. Okay, so you can build up structs from smaller structs. And if you want to set the height, let's say my snowman is called Snowbob, then I could say snowbob dot head dot width equals 4.4. Okay. So you use the dot operator multiple times in series to refer to a nested data structure. Okay. Structures can be passed as function arguments. I don't know why you would pass GPA to a function called compute GPA. If you already knew it, then why would you pass it? But you can also pass the entire struct variable to a function. So show data stew. This is actually probably the most useful thing you can do with structures is create a function. Once you've created a structure called student, you should create a function called display or show data or something that prints out all of the student variables, so you don't have to sit there every time you want to see a student and say cout what was the name of that variable. Yeah, cout what was the name of that that first field again. You can just say show data stew and it'll print it out for you. Okay, so here this person has created a show item function that couts the part number, the description, the units, and the price as 4 lines in a row that would help you when you're writing a program not have to remember all of that stuff at once or every time. Okay, using structures as function arguments. It's important to note that using these as value parameters, passed by value parameters, is pretty darn slow on a computer time scale. Okay, you're not going to notice it, but the computer will notice it as being slow. Since you're making an entire copy of the entire structure, if you have a fairly large structure, that can also waste some space. So passing it as a reference parameter, const inventory item and p means I pass a pointer to, or I pass a reference to the variable rather than copying the variable, and that's faster. We'll see in a few minutes that we can also pass the entire structure as a, or pass a pointer to the structure, and that also would work. More than one way to skin that cat in C++. A function can return a structure, and again, this is one of the main places where structures are incredibly useful in C++. Is if I wanted to write a function get stats and pass it an array of pass it double test scores as an array. Okay, Or I could pass it star test scores as a pointer. Either way, I have to then put int num scores, right? Because C++ doesn't pass how big the array is. What can, I want to get, I want to calc average, standard deviation, max, min. Maybe I have some other statistics that I really want to know about this. I can't pass all 4 of those values, right? But I can. I can create a struct stats double average, standard deviation, max, min. Okay, and then the return type for this function can be stats. So I pass in an array of test scores. I let the function cycle through all of my scores to find the average, the standard deviation, the max, the min, and then I return a stats object or a stats struct. Keep trying to get ahead of myself and use objects here. Note that you do have to actually create a temporary object of the right type so that you can then return it at the end. Okay, this program uses a function to return, you're getting the radius, diameter, and area of a circle. So you call getInfo, and the circle, the getInfo gets the diameter of the circle from the person, computes the radius as diameter divided by 2, returns temp circle. Okay. Pointers. We can certainly use pointers to structures. A structure variable has an address like any other. Okay, so if my student is sitting here with ID, name, year, GPA, each of these subfields has an address, but the whole thing might be at address 0004. And so then I can create a pointer, star student, I'll call it, that holds that address to point here. Okay. Must use parentheses to dereference the pointer variable, then specify the field within the structure. I couldn't just hit star stu pointer dot student ID. It would try to interpret that whole phrase as a pointer, okay? And that's not going to work. So I have to do this awkward thing. Since people got tired of doing that, C invented an arrow operator that combined dereferencing a pointer and looking up one of its fields. So this is stu pointer points to student ID, or stu pointer arrow student ID. That gets you what you're looking for in a much neater looking notation. So here we have another version of our get data function, but this time we pass a pointer to student so that any changes we make to S in the function automatically get carried back to the student that was passed to us, and we use S arrow name, S arrow ID, S arrow credit hours, S arrow GPA. All right, so that's about all we need to know about structures, but there is one other structured data type that we need to talk about really briefly called an enum, or an enumerated data type. When you think about enumerated data types, think about the things that you have in your regular life that you literally could count on your fingers that are, there are a certain number, a fixed number of things, and we know red, orange, yellow, green, blue, for example. Okay, those are an enumerated type. There are actually kind of an infinite number of colors out there, but if you want to talk about primary colors, we could list them on our fingers, right? And we could even assign them names if we wanted to. Numbers, we could call this color 1, color 2, color 3, color 4, and color 5, okay? And if you want to get blue-green, you mix a little 4 and a little 5, right? Sometimes there are things that really are not just you have cardinal value, cardinal values, but that they really do only come in a certain number of things. Jan, Feb, March, April, June, July, August, you get the picture, right? And these do have numbers. We refer to this as month 1, 2, 3, 4, 5, 6, 7. So these are enumerated types. Another excellent example of an enumerated type are the days of the week. There are 7 of them. In this case, they're picking 5. I guess they're just talking about the typical American work days, but and who works a normal Monday to Friday schedule anymore, I don't know, but my wife, who teaches high school. There you go. Okay. Monday, Tuesday, Wednesday, Thursday, Friday would be the days that she actually shows up to high school. It's not the only day she works. She grades papers like all the time. So the identifiers, Monday, Thursday, those are enumerators. They enumerate, they count out the possibilities for the day data type. Okay, note that these are not strings, so they're not enclosed in quotes. These act like integer constants. Okay, Monday is a named, it has now become a named constant that holds a value of the first day, or the 0th day, actually. As with everything else in C++, we start counting with 0. Okay, once you've created your enum type, you can define variables of that type using that same type name, variable name syntax. And then we can assign any of those enumerated values to workday. We cannot just give it a number. We can't say workday is day 2. We have to, if we've set up this enumeration, we have to use our enumerators to assign the type. Okay, now internally, the compiler assigns integer values to each enumerator beginning at 0. So if we say enum day, Monday, Tuesday, Wednesday, Thursday, Friday, the compiler says Monday, you're 0, Tuesday, you're 1, Wednesday, you're 2, and so forth. If we print this out, see out Monday, Wednesday, Friday, we'll actually get 0, 2, 4, because those are the internal values for the constants Monday, Wednesday, and Friday. However, it doesn't work the other way. We can't just say workday equals 3. We have to either do it the proper C++ way and use a static cast of type day on the integer 3, or we can do it the older standard C way and put our type name in parentheses and use that to operate on the number 3. Either way, we're forcing 3 to become a type day So we're producing the value Thursday because 0 is Monday. So 0, 1, 2, 3 gets us to Thursday. You can do it the other direction. You can assign an enumerator to an int variable. So x equals Thursday pushes the number 3 into x. Okay, why does it work one way and not the other way? I don't know. Enumerator values can be compared using the relational operators. So if the numerical value of Friday is greater than the numerical value of Monday, then, which it is, it will print this silly little statement here. Okay. This program demonstrates an enumerated data type. We're going to read in for index equals Monday to index equals Friday, index plus plus. We're going to step through the days in sales, but all we do is we print out day 0, day 1, day 2, day 3, day 4. I'll give you a solution to that in a minute. Okay, program 11.9 shows enumerators used to control a loop. So you can use the indexes that you get from Monday and Friday to power a for loop. You can also just use a type day as the variable in the for loop. We'll get to that in a minute. An anonymous enumerated type is one that doesn't have a name. This doesn't do anything useful at all. You'd have to actually give it a variable here. Like that. You can create an enum and then create a list of variables that it works with there. Otherwise, you've created an anonymous type and you can't use it to create a variable because it doesn't have a name. Note there is a problem in doing math with enum variables because you can't assign an integer to an enum. Okay. What this says is day 2 is day 1 plus day 2 is Tuesday plus 1, and the compiler says type mismatch. Okay. What you can do instead is cast day plus 1. What happens here is it's going to promote day 1 to an int, add it to 1, and then you're going to cast it back to type day. Okay, and that's the same thing that happens here. We cast this to an int, promote that to an int, that's already an int, but then we typecast it to a day. And again, you can use either of these. You can do it the more C++ proper way with the static cast operator, or you can do it the lazier way with the parens day. This one I happen to prefer because it's more universal. You can use that same syntax in C, C++, Java, C#, almost all of the C-related languages. Okay. Now, because enumerators are stored in memory as integers, you can use them as array subscripts. So you can say sales subscript Monday, read that as sales on Monday, is 1525.0. Can we use that in a loop? Well, we can set workday equals Monday. We can do that. We can say workday less than equal to Friday. That's fine. The error comes when we try to do workday plus plus. Because workday will, as soon as you plus plus it, you're going to promote that you get that problem. It's promoted to an integer so that you can add 1 to it, and now it's a type mismatch. So again, you can static cast it back to a day after you've added 1 to it. Okay. Okay, and so here's an example of using that syntax to work through the same loop that we'd done earlier. Okay, now I mentioned that if you see out which day it is, if you see out a day variable, it's going to give you 0, 1, 2, 3. It's not going to give you the name of the day. A really easy way to handle that is because an enumerator, because an enum variable is an integral type, okay, enumerators work really handily with switch case constructs. So if I have a day called which day is it, I can do a switch on which day is it, and if that turns up Monday, I can very easily print it is Monday. If it turns up Tuesday, I can print it is Tuesday. So this takes up a little bit of code space, but it's very easy to generate something that prints out the correct day depending on the value of that day variable. And in fact, there are some IDEs that as soon as you type switch which day is it, they will auto-populate case Monday, case Tuesday, case Thursday, case Friday, because they know those are the possible values. One little caveat. Enumerators, because they are instantly created in the compiler as named constants, they have to be unique within the program scope. So I can't have an enum with Roosevelt and a vice president with Roosevelt, okay, because that would declare the same variable to hold two different values, the same constant to hold two different values. In C++11, they allowed you to create a enum class, which makes the enumerators subclasses or within the scope of the enum name. So now I have one identifier, presidents : Roosevelt, and another one, vice presidents : Roosevelt. The : is the scope operator. It says Roosevelt. Which Roosevelt? The one in the scope of presidents. Which Roosevelt? The one in the scope of vice presidents. Okay. And finally, we can, as we saw when I did the anonymous enum earlier, we can define an enum type and have a list of variables in the same, on the same line or in the same statement. Enum car is either a Porsche, Ferrari, or a Jaguar, and the variable name is sports car. You can have a list of sports cars. You can have an array of sports cars, okay? All right, so that sums up what we need to know about structured data types. We've now finished all of the pieces of C++ that are basically equivalent to something in the C language, okay? Next time we start on objects and classes, which are the things that make C++. They're the plus part of C++. They're the part that makes it a new and unique object-oriented language. Okay, thank you for your attention. As always, if you think you learned something, give me a like, give me a comment in the comments below. I always like to hear from people. And keep studying.